Hello, and for this video we're going to be covering the video number 4. So it's going to be the polar form of complex numbers. So 1.4 we're going to be covering complex numbers in the polar form. So first of all, if we say we had a complex number z equals to 1 plus I, if we have the complex number written in the form of a real number plus a real number times I, then this will be known as the rectangular form. So this is rectangular form of a polar number. However, there are also other ways to express complex numbers, and polar form is another way to express a complex number. And we can say that 1 plus I can be represented differently, but it's still 1 plus I, but we just represent it differently in a polar form. So if we relate back to the Argand diagram we saw in the last video, so let's say we have an Argand diagram. Alright, so if we have our Argand diagram, so we say this is the imaginary part of z, and this is the real part of z. If we were just asked to plot z into the Argand diagram, we saw pretty confidently how we could do this in the last video, 1.3. So z would be around, we say around there, 1 and 1, and that would be z. So if we were to express z as 1 plus I, like I just said, that would be the rectangular form. However, we can also express z in the polar form. So we can express z if we draw a right angled triangle from the origin to z. We can say that z can also be represented by the length of the line from the origin connecting the position of z to the origin. So we can say that this length we're going to be called the modulus of z. So we have this length of this line here, that will be the modulus of z, and that was going to be represented like this. So that, if we see this notation with two lines in between the z, that will be equal to the modulus of z. And the modulus of z, okay, that's basically, you can just think of it as the length of the line connecting the origin to the complex number. And we can also see that there's an angle theta from the real axis to the line connecting the origin to the complex number, and we're just going to call this angle theta. And therefore we can represent this complex number z in the form of equals to r cis theta. You might also see in some other textbooks that it can be rewritten as r e to the power of I theta. However, for the terms of NCA, we don't really need to worry about that. We just need to worry about the expression r cis theta. So in this case, what is r? R in this case is the modulus of z, so r is directly referenced to the modulus of z. And theta, that will just be the angle that we see here, the angle theta. And this will be, in this representation, we can rewrite 1 plus I in this representation. So how would we do this, just to convert simply between rectangular form and polar form? Well, if you want to do it directly, first we can calculate the length of the modulus, and we can calculate the angle. So what is the length of the modulus? So we should learn from around year 10 Pythagoras theorem. We can find out the length of the hypotenuse of a right angled triangle. We can use Pythagoras theorem, so that's a squared plus b squared equals c squared. The length here is obviously 1, because our length from the origin 0, 0 to the point 1, 0, that is going to be a distance of 1, and then the distance from the origin 0, 0 to the point 0, 1, that's going to also be length of 1. So in this case, we're going to say that 1 squared plus 1 squared equals to c squared. So c equals to square root of 2. So we can see here that our r in this case would be square root of 2. What will be our angle theta in this case? Our angle theta is simply, we're going to be using some trigonometry here. So we have tan theta, that's equal to the opposite side over the adjacent side of a right angled triangle. So tan theta equals to the opposite over the adjacent. So tan theta will be equal to 1 over 1. And if you solve for theta, so theta equals to the inverse tan of 1, and theta will be equal to 45 degrees. However, this isn't really a requirement in CA, but it's also always the best idea to convert your your angle theta into radians form. It's just because that is the standard way of notation for mathematicians. However, I believe if you're only working at NCA level 3 level, they don't really care if you use degrees or radians. However, just for more common notation, it's recommended that you do use a radians form. So 45 degrees, that is exactly the same as pi over 4. So that's exactly pi over 4 radians. So in this case, we can rewrite z as square root of 2 cis of pi over 4. And what exactly is cis, you might be asking? So cis is simply cos of theta plus I sine of theta. So if we rewrite this complex number here, we can see that z is actually equal to square root of 2 times of cos theta plus I sine theta. And in this case, theta is pi over 4. So you say z is equal to square root of 2 cos of pi over 4 plus I sine pi over 4. And if you have a calculator, you can actually compute this value. If you have a calculator, cos pi over 4 plus I sine pi over 4, that should really just give you back the rectangular form, which is 1 plus I. Alright, so converting from, so that's what you usually be doing if you're converting from rectangular form to the polar form. And if you want to convert the other way, from polar form to rectangular form, it's pretty simple. So if we just have here, if we had, for example, if we just said a complex number is z equals to, we say 2 cis of pi, for example. So what you would do is, you know what cis was, I just told you is cos theta plus I sine theta. So that would be z equals to 2 times of cos of pi plus I sine of pi. And you can just, if you're not familiar with exactly the values of cos of pi, you can just use your graphics calculator. But in this case, cos of pi is -1, sine of pi is 0. So this will give us just -2 plus 0i. But you don't need to write the 0i, it's just -2. So that's an example of converting to the converting from polar form back to rectangular form. And one more thing to note that I forgot to mention is that the angle theta is always counted anti-clockwise from the positive x-axis. So for example, if we had, let's say we had this here, and let's say this was 45 degrees. So in this case, this angle theta is actually -45 degrees, since we're actually counting it from if we count from the positive x-axis, we're actually going in a clockwise direction, which is the opposite way of the anti-clockwise direction. So if you're going the opposite way, that's going to give you a negative sign. And notice that if we say that, for example, we just say the modulus here is just say it's r. We don't really care about that right now. We just say the modulus is r. So we say this complex number, we call it z. So we say z equals to r cis of -pi/4. However, notice that if we drew an angle from the positive x-axis all the way to the complex number this way, then that is actually going to give us exactly the same complex number. So there's actually there's actually an infinite number of ways you can express this complex number. Since, for example, if we said z equals to r cis of, instead of -pi/4, instead we count from the positive x-axis to this complex number, we should get, if we do the math properly, we should get 7pi/4. Hopefully I did that right. So you see that these two numbers are exactly the same thing, because it doesn't matter if you're going from the positive x-axis anti-clockwise to reach your complex number, or you're going from the positive x-axis to the complex number. In NCA, they don't really mind what notation you're using. If you write this and this, they're just going to treat it as exactly the same. However, it's good practice to always restrict your absolute value of the theta to be less than pi. So in this case, our preferred notation, I would say, is r cis -pi/4. However, like I said before, in NCA they don't really mind. And like I said before, there's actually an infinite number of ways to express this complex number z. Why is there an infinite number of ways? Well, if you notice that if we go from the positive x-axis anti-clockwise to this complex number, notice that we can just go another round of circles. So instead of stopping here, we just go another 360 degrees. So this is exactly the same as saying r-cis of 7 pi over 4 plus 2 pi. Exactly the same thing, because by going 2 pi and go around, you're just ending up in the exact same place. You haven't moved at all. So in fact, you can add as many of these 2 pi's, or you can take away as many of these 2 pi's as you want. It doesn't matter, you're going to end up at exactly the same place. So that's why I'm saying that there's actually an infinite number of ways to express this complex number z. So technically, I can write it as r-cis of 7 pi over 4 plus 2n to 2 plus 2n pi, where n is any integer, really. So n is like an integer. However, when you're expressing the complex number, make sure it's always in its easiest form. When I say the easiest form, I mean that the absolute value of the angle should be less than 2 pi. So if it's not less than 2 pi, that means you can always take away a full revolution of the circle and then be left with something that's smaller. So always remember that you should leave it in the most simplest form. So when I say most simplest form, I just mean that the absolute value of theta should be less than 2 pi. Alright, so maybe we just have a couple of our quick practice ones on conversion. Shouldn't take us too long. So let's say we have z equals 2, say 2 cis of, say pi over 4. So what is that in the rectangular form? So we're just going to write this out as 2 times of cos of pi over 4 plus I sine pi over 4. And like I said, if you're not too confident with the calculator, if you're not too confident with memorizing the exact values of cos of angles, then you can use your calculator. And both of these will just give us root 2 over 2. So that's just root 2 over 2 plus I root 2 over 2. So that would just be 2 times of everything inside. So that's just root 2 plus I times root 2. So that's an example. Let's give one more example before we leave off this video. Maybe we say that z is equal to, we'll say, 1 minus I. Okay, let's convert 1 minus I to the polar form. So for these questions, when they're asking you to convert to polar form, like this is just like a personal thing, you don't have to do it, but I always just like drawing out an Argand diagram. I like drawing this Argand diagram out and then plotting the point just to get a visual representation of where this point lies. So 1 minus I would say that's around there, and that would be our angle theta. So what is our modulus? Our modulus of z is actually the length of the line connecting the origin to the complex number. And remember, we're using the absolute value of the length here. Okay, we're not just negative. It's not actually a negative. Well, it is a negative in a sense, but in terms of the length, we're going to take the absolute value. So in this case, this is going to be 1 squared plus, well, negative 1 squared is positive anyway, but sorry. So modulus of z squared equals to 2. So modulus of z is just square root of 2. And the angle theta, we're going to say that tan theta is equal to, and remember this length is 1 and this length is also 1, so we just say tan theta is equal to 1 divided by 1, so theta equals to pi over 4 or 45 degrees. Alright, so remember what I was saying before, that this is actually negative pi over 4 since the notation is to count anti-clockwise from the positive x-axis. So in fact, this complex number z is actually square root of 2 cis of negative pi over 4. Alright, and that's just a couple of examples on converting between forms, and I hope this video makes it clear the polar form of a complex number, and we can distinguish it between the rectangular form. And I hope by the end of this video you can understand how to confidently convert between the polar form and the rectangular form, as well as understand what the geometric representation of a complex number in its polar form. Thank you for watching.